our journey of learning Laplace transform. So today I'm not going to do anything new. We are already halfway through our course on Laplace transforms. Uh, what I will do today instead is take a quick review of what we have done till now. So everything we have done, I'll recall. So in case you have missed something from the previous classes, you'll be able to understand this. Only a little bit. Most of it, if you haven't understood most of it, you have to see the previous lectures. Because I hope most of you are not in that state. So whatever little bit you may have some doubts, it will get cleared in this lecture, I hope. So what did we do? We defined Laplace transform of a real function ft, which was defined like this. Laplace of ft is e power minus st ft dt, integral of this. Integral limits t varying from 0 to infinity. Observe that Laplace is a transformation, or it's sort of function of a function which takes functions in independent variable t and returns functions of s. We have seen this. Just to emphasize, I'm telling this again. You see here, this ft is some particular function of t. When I multiply by e power minus st, I'll get a function in both s and t. And I'm integrating with respect to t. So I'll get, when I integrate, I'll get a function in both s and t. But then I'm substituting limits of t as 0 and infinity, which means t is no more, you can't see that t in the expression. So I'll be left with only s. So the resulting expression is a expression, or it's a function in s. Our s and t are related, really there is no relation. So both are two independent variables. So L of ft is f of s, and this is a standard notation. All through this course we have been using this and we will continue to use this. Whenever I write capital Fs, it's understood there is a small function f whose Laplace transform happens to be capital F of s. It's just a notation. We will keep using this very often. So L of ft is f of s. The point to be observed, L is a transformation which takes functions of t as input and returns functions of s. This is the bottom line. And one of the most important properties which we have exploited, which we have used, is linearity. Laplace transform is a linear transformation, which means if you give me two functions, f and g, L of f of t plus g of t is L of ft plus L of gt. And similarly, if you give me any real number or even complex number, L of a f t is a times L of ft. So these two properties together constitutes what is known as linearity property. Since Laplace satisfies these two properties, we say Laplace is a linear transformation, Laplace transformation is a linear transformation, and we write it in one code. L of a f t plus bgt is a L of t plus b gt. We have used this in and out to find Laplace of various functions. And then we found the Laplace of some very elementary functions. The proof of this is not very near exam, but then you should know the proof. It's not difficult. I have given you these proofs in the lecture. Laplace of constant function 1 is 1 by s. Laplace of e power at is 1 by s minus a. Laplace of sin at is a by s square plus a square. Laplace of cos at is s by s square plus a square. Sin is a by s square minus a square. Laplace of hyperbolic cos s by s. Laplace of tau n, where n is an integer, is n factorial by s to the power of n plus 1. And when n is not an integer, any number bigger than minus 1, p power p, it is gamma p plus 1 by s to the power of p plus 1, where gamma is the gamma function. So these, for your examination purposes, these 8 will suffice. If you want, as I said, you can check on the net or some standard textbooks. You will find Laplace transform of various functions. For your examination purposes, these 8 are sufficient. That was 7 are sufficient, mostly. And then what did we do? Apart from finding Laplace transform of these standard functions, we picked up functions from standard functions, from elementary functions, and tried to find Laplace transforms of those functions. For that, we used linearity and table of Laplace transforms. Let me recall what we did there. Something like this. Find Laplace transform of 5 minus 4 e power 5 minus 7 sine 2t plus e power minus 8t plus 7 to the power of t. So this is a function of t. Now I want to find Laplace of this. How do I do that? Basically, I use linearity and the table of Laplace transforms. They are the only two things which we know. So Laplace of this given function is essentially Laplace of each term added or subtracted accordingly. Whether you are adding this term here, you are subtracting this term here, you are adding this term. So accordingly, we write Laplace of each term. Laplace of 5, Laplace of 40, minus Laplace of 40 cos 5, minus Laplace of 7 sin 2t, etc. etc. How do I evaluate this? I pull out constants. This is true. This first part is true because L of ft plus gt is L of ft plus L of gt. That's what I have used here. And for the second part, I will pull out the constants. So pulling out the constants, I get this 5 L of 1 means 5 means constant function 5 is same as 5 times constant function 1. Similarly, 4 if I can pull out, 7 I can pull out, etc. etc. Here I can pull out also. And now Laplace of 1 t power 5 sin 2t t power minus 8t, and this is a bit of a I'm sure you all know this 7 power t is same as e to the power of t log 7. I'm still doing it for the last couple of years, such things. So I have 7 power t, I have written it in a form for which I can find Laplace very easily. That's essentially what I have done here. So now I know Laplace of each of them, and I just write it down. For Laplace of 1 is 1 by s, Laplace of t power 5 is 5 factorial by s power 6, Laplace of sin 2t is 2 by s square plus a square, a is 2 here, and Laplace of e power minus 8t is 1 by s plus 8, e power 8t is 1 by s minus a, and here a happens to be log 7, so it will be 1 by s minus log 7. As I said, don't try to evaluate this or simplify this, just leave it. This is like for us to try to simplify it. So essentially we have used linearity of Laplace transforms, and we have used table of Laplace transform, which gives me standard Laplace of standard functions. Would you need table of Laplace transform in the exam? You have to remember these things. The only way to remember is to solve a few problems, then automatically you remember Laplace of sin 80 is a by s square plus a square. Laplace of cos 80 is s by s square plus a square, etc. You remember these things only if you solve a few problems. And then I did not do it, I did not show explicitly this kind of example when giving the first time. So now I am going to do this is cube of hyperbolic sine function. I told you what is the rule to find any power of hyperbolic functions. If I want to find Laplace transform of that, how do I do it? Just use the definition. Here, sin h2t is nothing but e power 2t minus e power minus 2t by 2. This is the definition of hyperbolic sine. Those of you who still haven't understood this, please understand this. This is a formula. This is actually the definition of hyperbolic sine. This is e power 2t minus e power minus 2t by 2. So now take cube. So cube it of a minus b whole cube, which is a cube minus 3a square b plus 3ab square minus b cube. So that's what I have done here. So e power 2t whole cube will be e power 60 and 3a square b. So 3 I have written minus 3a square b. Minus 3 I have written. Then a square is e to the power of 4t into e power minus 2t, so I have e power 2t, and similarly plus 3ab square. So 3a is e power 2t, b square is e power minus 4t, so I have e power minus 2t, so plus 3 e power minus 2t minus e power minus 2t whole cube, which is e power minus 60 divided by 8. So if you want to find Laplace of this, use linearity. So Laplace of cube of hyperbolic sine 2t is Laplace of this variable. And that how do I evaluate? Pull out 1 by 8 and I get Laplace of e power 60, etc. etc. These things we know. Laplace of e power 60 is 1 by s minus 6. This is this 1 by s minus 2, etc. etc. So, usually, so basically remember, you need to know the definition of sine, hyperbolic sine, and expand it and find Laplace of each of them. Use the standard table. Before you need to use the fact that Laplace is linear. I'm using linearity very heavily here. See, every step from here to here to come from here to here, I have used linearity. Of course, I used twice already. I pulled out constant also, and I have broken up the given function into some functions. So that is what that's the main property of Laplace transform. And then I also told, of course, I told several examples about powers of sine, powers of cos, not all powers, sine square, cos square. In that case, we use the property, the formula which says cos 2t is cos square minus sine square, which is same as cos 2t is 2 cos square minus 1 or 1 minus 2 sine square. So we use this formula if there is a term of the type, if I want to find Laplace of sine square 5t and things like that, or cos square 7t, something like that, cos square 80, sine square 80, we use that formula and do it. And then we came across this kind of formula where this kind of expression where I needed to find Laplace of product of sine and cos, maybe sine or cos or sine cos, whatever. So these are the three formulae which you must remember. This somehow you must remember this, and please cross-check whether I have written correctly. Mostly I think the first time once I have written a little bit wrong and minus I had missed out. I hope I have done the correct thing now, but still I request you to check this once. So sine AT, sine BT is half cos of A minus BT minus cos A plus BT. How is this useful? So if I am trying to find Laplace of sine A into sine B, sine AT into sine BT, which is same as Laplace of this whole thing. That is easy to find because now I use linearity, I pull out half, and Laplace of this is half Laplace of this minus half Laplace of this. Laplace of this I know how to find. Laplace of cos some constant times t is s by s square plus this constant square, and similarly for this. So then I can find by using linearity property of Laplace transform, I can find Laplace of sine A sine B. Sine A t sine B t. Similarly, sine A t cos B t. So that also has a formula in terms of sine A plus B and A minus B. Similarly, cos A cos B. Cos A t cos B t, if I want to find Laplace, it is half Laplace of cos A plus B t plus half cos A minus B t. So this again I can find in similar case. So these are the standard techniques to find Laplace of various functions which are built from elementary functions. This is an important point. One may have to use these repeatedly. For example, if I have a term like sine AT, sine BT, cos CT, then what do? First, I expand using this formula, sine BT into cos CT. I can expand using this. So I get two sine term. Multiply that by this sine A outside, so I get sine square and but not sine square. I'll get something sine into sine minus sine into sine of different arguments are different. So sine into sine, I use this formula. So we use this formula twice. One of these formula twice, not one, maybe twice. You have to use these three formula. I mean, one of these three, or two of these three. That's how I should put. Two of these three formula you have to use twice. Then you will get answer for Laplace of three terms, the product of three terms, sine, cos, or sine. Sine is okay, but if arguments are same, it is sine cube. That I'll show you how to do it. If it is sine 5t, sine 3t into sine 7t, something like that, then you have to use this formula twice. I gave you an example, two examples I gave before, so I don't think I'll spend time on that. I did not give example for this cubes of sine and cosine. I just told the method and then that's it. So maybe now that we have some time, I will try to explain how to find Laplace of cubes of sines and nothing much in this also. It's the same thing. Use linearity and one of the usual trigonometry formula. So here is an example. I want to find Laplace transform of cos cube of phi t. Of course, you can try to use cos phi t into cos phi t into cos phi t and use this horrible formula twice. Cos a is also 5 and b is also 5, so this will become 0, then I'll get 1, etc. etc. You can do it. The easier thing is to use formula. Cos cube 80 is 1 by 4 3 cos 80 plus cos 380. Similarly, sin cube 80 is 1 by 4 3 sin 80 minus sin 380. You must have seen these formula when you studied the sine of 3x. Sin 3a is something, right? 3 sin a minus 4 sin cube a. That you must have seen in your PUC. So that is what we are using. But here I am solving for sin cube. There we were solving in this left hand side was sin 3x. Here left hand side is sin cube x. That's all the difference is. It's the same formula. So here cos cube phi t. So use the formula cos cube 80 is 1 by 4 3 cos 80 plus cos 380. It is not. If you don't know this formula, it's very difficult to solve this problem. So you must be very familiar with all your trigonometry formula. So Laplace of cos cube phi t is nothing but, now I use linearity of Laplace. 3 by 4 Laplace of cos phi t plus 1 by 4 Laplace of cos 3 times phi t, that is 15t. Both these I can find. Cos phi t I know how to find. This is s by s square plus phi square. This is 15 by s square plus 15 square. So I just plug in those things. That's all. Over. Problem over. Laplace of cos cube phi t is 3 by 4, etc. etc. So again, just nothing much we are doing. Just use one of these old formula which you have learned in your PUC, and then use linearity. I want you to what I want you to observe is this is the same thing we would have been doing if you wanted to integrate. Like let me emphasize this. If instead of the question find Laplace transform of cos cube phi t, the question was find integral of cos cube phi t. What would you do? Same thing would you do. Instead of L, they will have been I. So I of cos cube phi t is 3 by 4 I of cos phi t plus 1 by 4 I of cos 15t. These are easy to find. I of cos phi t and I of cos 15t is direct straight. So that's what you have been doing. If you are asked to integrate, same technique we will follow to find Laplace transform. After all, this is also an integration, if not of the function directly. You multiply the function by e power minus t. So nothing very big about what methods we are trying to do. It's the same. Then we saw, so these are the first principles were basically use linearity and try to compute Laplace transform of different kinds of functions. Functions made out of elementary functions. Not because all elementary functions, some are difference of elementary functions. We never asked Laplace transform of e power t divided by sin t. That kind of, there's no multiplication also. E power t into sin t, how to find Laplace transform? Because multiplication is not a very nice operation in calculus. Calculus operations do not respect multiplication. You know very well the differentiation of product of two functions is not the product of differentiation of functions. So there's a Leibniz which is easy, but it's not straightforward. So similarly for integration of product of two things is not product of integration. So you have to struggle a bit more. The formula is a bit more complicated. Similarly, if you have we can't so easily find Laplace of product of functions, but we can find Laplace of sums and differences. That's what we have done. Sums and differences of elementary functions. That's what we have done. Now, so next we saw a list of properties of Laplace transforms, which actually expanded our horizon on finding Laplace of functions. More different, more complicated functions we could find Laplace of. So what were those properties? These were the four properties: change of time of scale, change of scale property. Obvious name because it just says scale, changing this time. Time, if f of t, L of f of t is f of s. Now in this formula you get to know what is L of f of a t. That means t is multiplied by a t. So that's how you change the time. So then what happens to Laplace is it is 1 by a times capital F of x by a. Remember this notation, this is very important. This is a notation, but it's a bit confusing at times. So L of ft, L of small ft is capital F of x. This is, if you forget your name, you cannot forget this notation. Laplace of small ft is capital F of s. And the second rule was shifting rule or change of frequency rule, which says Laplace of e power at into ft is capital F x naught. See here one illustration of what happens when you take product of two functions, not arbitrary functions. One of the functions is e power at. And here we don't get Laplace of e power at equal Laplace of ft. No, we don't get that. Don't respect that. Instead of that, what it does is you take Laplace of this small f and replace s in that by s minus a. That is what this formula says. So the power of this formula is that if I know Laplace of ft, I know Laplace of e power at into ft. That is precisely what is the power of this formula. If I know Laplace of ft, which is capital F of s, then Laplace of e power at ft is same as Laplace of ft, but instead of s you write s minus a. Where did a come from? A is from a. This follows straight from definition. The proof of it is very easy, straightforward. It's not there in your syllabus, but please do it once. And then Laplace of e power n ft is, this is like this, whereas now instead of multiplying by e power at, I'm multiplying by e power n. So when I do this, I'll get this formula, which is Laplace of p power n ft is minus 1 power n nth derivative of capital F of s. That means saying f of s, we differentiate n times and change the sign depending on n is odd or even. That is the answer for Laplace of p power n into f. The most important case in general, theoretically we know, and if you know Laplace of ft, I know Laplace of p to the power of 100 into ft also. All I have to do is differentiate 100 times, so that's easy. But anyway, theoretically I know that. Most useful part of this formula is when n equal to 1. When n equal to 1, I have written down this formula explicitly. So if you put n equal to 1, I get L of t is minus first derivative of fs. That's what it's written here. Laplace of t is minus first derivative of fs. So this is a very useful formula because whenever you want to multiply a function by t and find its Laplace, this formula is going to be useful. And then finally we have Laplace of ft by t. When I divide ft by t, what happens to the Laplace? It becomes this integration of Laplace of ft. That's what this formula says. I want you to see a relation here. You see, differentiation and integration are inverses of each other. That's how you are taught integration. Integration is reverse process of differentiation. Similarly, multiplication is a reverse process or inverse of division. So here when you take division, it becomes integration. When it is multiplication, it becomes differentiation. These are very deep consequences. Not for your course, but if you study deeper mathematics, you will see this is not coincidence. This is something which is sort of planned out. The theory came after people saw these particular cases. So L of t is minus d by ds fs, and L of ft by t, you can think of ft by t is L of t power minus 1 ft. So here minus 1 times differentiate means integrate. That is how, in some way, since one can try to remember both this formula in one shot. Let me recall. Laplace of ft by t is Laplace of t power minus 1 into ft. So that means it's like Laplace of t power n into ft where n is minus 1. Minus 1 means here you take minus 1 of derivative means integrate. That's precisely what we are doing. But with limits s to infinity. Anyway, this just ways to try to remember these formulas. But in any case, you have to remember all these four formulas. Definitely, these last three are very crucial. L of e power a t f t is capital F of s minus a. Laplace of t power n f t, particularly L of t f t, is minus d by ds f of s. Laplace of f t by t is integral of f of s from s infinity s to infinity. Let us solve several problems based on this very elementary ones. For example, if it's very easy to find Laplace of ft, I would ask find Laplace of e power a t ft. Typical example would be find Laplace of e power 5t into sin 3t. So you know Laplace of sin 3t. So in that we replace s by whatever s minus a, where a is e power a. A comes from e power a t. Similarly, this also, if I know Laplace of ft, then I know Laplace of tft. Try using it for polynomials. It's quite interesting. So take what I meant is, means I'm not going to write it, but I would expect you to do it. If ft is say 1, then Laplace of t into 1 is Laplace of t. That must be minus d by ds of f of s. What is f of s? When it is 1, it is 1 by s. So derivative of 1 by s with a negative sign, it is 1 by s square, which is correct, which is negative. Similarly, we try to find Laplace of all t power n. Laplace of t power n is Laplace of t into t power n minus 1. So now t power n minus 1 Laplace is what? Try to find it by reduction or something like that. So this gives you a proof of one of the things which we did before. Laplace of t power n is n factorial divided by x to the power of n plus 1. You can try such steps. And Laplace of ft by t is integral. So if I know the integrating Laplace of ft is easy, then I can find easily Laplace of ft by t. So anyway, let me show you some examples which are very easy. It's not at all difficult, but they look different from what I showed you before. So let me write down here. Here it is. Show that Laplace of cos h at into ft is 1 by 2 capital F of s minus a plus capital F of s plus a. This is one part. Second part is show that Laplace of sin h at into ft is half capital F of s minus a minus capital F of s plus a. There are two problems here. And then using hence evaluate, that means use these to evaluate Laplace of cos h at into sin b. So what does you come to these? I mean, we'll go slowly. There are three parts, three problems here. So you will see if you solve one, the others will follow. In fact, you see this problem is a particular case of this where ft is sin bt, and I know Laplace of sin bt, and then I replace b by s minus a, s by s minus a, and that's all. So what I'm trying to say is these problems are related; they are very similar. So let me start with this. Let me first Laplace. So what is this? This says when I multiply a function by hyperbolic sine or cos, then I know I can find Laplace very easy. That's what this statement says. If I know Laplace of f, I know Laplace of hyperbolic cos into f, or I know Laplace of hyperbolic sine into f. I have to just follow this formula. Very interesting to remember this formula. You can very easily derive this formula. So let me show you how to do that. First, let me do the first one. The first one says Laplace of cos h at uh, ft is half uh, capital F of s minus a plus capital F of s plus a. So this is the standard notation. I just told you, but I would not recall now. But this is pretty straightforward. Laplace of small f t is capital F of x. So let's do the first one. So the first one is Laplace of cos h at ft is half of f of s minus a plus half of s plus a. That's what I'm trying to prove here. So how do I go about it? Remember, I told you this before also. Whenever you see hyperbolic cos, just don't bother. Use the definition. Because hyperbolic cos is just a notation for that e power at plus e power minus at by t. It's another notation for exponential function. That's all there is, nothing else. So let us use that directly. That means I want to find Laplace of this, which means I replace cos h at by half e power at plus e power minus at. So Laplace of this is Laplace of this. So how do I find that? Now I'll open out the bracket, I'll expand this. So I'll get, and at the same time, half is of course a constant, so I can pull it out of L. So that's what I have done. Half L e power 80 into ft plus half L e power minus 80 into ft. So just use linearity of Laplace transformation. That's all I have done. Using linearity of Laplace transformation, I did this. Now, do I know anything about Laplace of e power 80 into ft? Should ring a bell. What is the bell? Here is the property which we are looking for, which is very important, I think. Laplace of e power 80 ft is capital F of s minus a. So if I know, that's what, moment you see that, you should remember. If I know Laplace of ft, I know Laplace of e power 80. So that is what we are using here. So now Laplace of e power 80 ft is what? If I know Laplace of e power ft, which I know because I have given it as capital F of s, then I know Laplace of e power 80 ft. So that means this is nothing but capital F of s minus a. This is actually directly that formula which I told is very important. Or nothing else to do. Similarly for this e power minus 80 ft, you replace a by minus a. So you get f of s plus a. Laplace of e power minus 80 ft is capital F of s plus a. These two follow because that is the formula. Formula is e power 80 ft. Laplace of that is capital F of s minus a. So that I written that. That's all. Over. So what has been asked to prove has been proved. Laplace of cos h 80 ft is half capital F of s minus a plus capital F of s plus a. It's as simple as that. Now, similarly for sin HAT. Sin HAT also is the same thing. What would have happened? I would have used definition of sin HAT, which means it's the same thing except that this would have been a minus. If this is minus, then this is also minus. If this is also minus, so that is precisely what that formula was. You see, it's the same for cos HAT or sin HAT. Right hand side is same except that this plus becomes minus. So that's basically because sin h 80 is e power 80 minus e power minus 80 by 2. Cos h 80 is e power 80 plus e power minus 80 by 2. So the plus is showing up here as plus and this minus is showing up as minus here. That's all. So you can very easily see these proofs. They are very simple and straightforward. Now using this we want to evaluate cos hyperbolic 80 into sin bt. This is product of a hyperbolic cos and a normal sine, usual sine. Product of hyperbolic cos and usual sine is what we have done. So use that formula now, whatever we just now did. In fact, the problem itself says hence evaluate. We use whatever we have proved just now to evaluate this particular Laplace. So we use this formula. Laplace of cos h 80 ft is half capital F of s minus a plus half capital F of s plus a, where ft is sin bt. If I replace ft by sin bt, I'll get this. So that means I'll have to first find Laplace of ft, that is Laplace of sin bt, that I know by the table. It is b by s square plus b square. In this, I will replace s by s minus a if I want to get this. Because this is nothing but capital F of s minus a. Capital F of s is b by s square plus b square. So f of s minus a is b by s minus a whole square plus b square. And similarly, f of s plus a is b by s plus a whole square plus b square. So add both of them and divide by 2, take average of the 2, and you have ended up with Laplace of cos h 80 into ft. That's what we will do. I hope it's clear. It's all just straightforward plugging in formula. There is nothing in this. Even not much formula also. It is definition of sine hyperbolic, cos hyperbolic, and that shifting rule. Shifting rule, it said Laplace of e power at ft is capital F of s minus a, or capital F of s is Laplace of small ft. That's all we have used, nothing else here. But what I wanted to appreciate is even though those formula are very few and very simple, together they make up a grand structure. There's so much of symmetry in all these things which we deal with. So that's what makes this part of mathematics interesting. After all, it's very useful in solving differential equations. Similarly, one can evaluate product of sine or cosine with hyperbolic sine equation. So there's nothing special about cos h at sine bt. I could have given you cos at and sine h bt. In sine h bt and cos 80. Then I would have had to use this formula. Which formula would I have to use? This one. Here I have proved whenever you multiply sine hyperbolic with some function, what is the Laplace? So if in particular ft is cos dt, that means sine hyperbolic 80 cos dt, then I just know Laplace of cos dt and done. I have to replace in cos dt s by s minus a. That's how you get sine hyperbolic 80 into cos dt. Similarly, sine hyperbolic into sine also you can do. It's just a capital F will change. So basically any product of hyperbolic function with normal sine function, then you can use this formula. And nobody remembers this formula, it's very easy to derive. Basically, we use the definition of sine hyperbolic sine and hyperbolic cosine. That's it. So all this we are done. So this is another problem. Find Laplace of 1 minus cos 3t by t. So how to do this? So I'll observe that this function is the form, the given function whose Laplace I want to find is of the form ft by t. So how do I find Laplace of ft by t? Oh, I know a formula. What is the formula? It's the integral of capital F of x. What is the formula? This is the formula. So whenever I have Laplace of ft by t to be found, I just need to find Laplace of f and be able to integrate that. That is the important thing. So basically you should know how to integrate. Otherwise these problems will make even more difficult. So Laplace of ft by t, so remember this formula. Laplace of ft, we have already used this formula several times in the number 3 or 4 or something. Oh, lesson number 3 I think. So Laplace of ft by t is integral of Laplace of ft from s to infinity. This is what I use. So in the given problem, it is 1 minus cos 3t by t. So ft is 1 minus cos 3t. So can I find Laplace of 1 minus cos 3t and then integrate that? That becomes a problem. So that's basically a PUC level problem. So let us check that, how to do that. So this is the problem. 1 minus cos 3t by t. I want to find Laplace of this. So I use this formula. Laplace of ft by t is integral of f of s ds from s to infinity with ft equal to 1 minus cos 3t. If ft is 1 minus cos 3t, what is capital F of s? That means what is the Laplace of this? Laplace of this is capital F of s. Laplace of this is Laplace of this minus Laplace of this. Laplace of this means Laplace of 1 is 1 by s. Laplace of this means Laplace of cos 3t, which is s by s square plus 3 square. So I have two terms in capital F of s. Laplace of 1 minus cos 3t has two terms. One is 1 by s, another is s by s square plus 1. Now Laplace of this ft by t, I am using this formula. Laplace of 1 minus cos 3t by t is nothing but integral of Laplace of 1 minus cos 3t. Laplace of 1 minus cos 3t, I just see it's 1 by s minus s by s square plus 9. So I have to integrate this. That's our biggest job now. How do I integrate this? So let us check. 1 by s, I know integral is log s. So s by s square plus 9, what is this integral? Remember how to do this? I'm sure you know how to do this. The numerator is derivative of denominator. with a factor 2 missing, so you multiply and divide by 2. So I get a half into 2s by s square plus 9. Then numerator is derivative of denominator. So then the integral of the whole thing is log of the denominator. So minus half will remain outside and it will be log of s square plus 9, and everything between the limits s to infinity. Lower limit of this is s, now higher larger limit is, upper limit is infinity. Let's see how to evaluate this. So a priori it looks a bit pathetic because you see infinity is always going to be a bit careful. This is what I told you in one of the first lectures, initial lectures. That lot of things in Laplace is looks like improper integral and things like that. But they never ask a question where it's actually really improper. Even though it looks like improper, it is not improper. So I will show that again. I showed you these kind of examples once before. There's some more subtlety here, so I'm showing you this thing. So how to evaluate this? This is basically an algebra problem, not even calculus. It's an algebra problem. So log s minus half log s square plus 9. Somehow I want to put these two together. Log a minus log b is log a by b. I want to put them together like that. So what I will do, I'll write log s as half into 2 log s. Why do I do this? Then I can take this 2 up here and call it half log s square. Right? That's what I have done here. Oh, I have not done that here. So I'll call this half log s square, and I can pull out half common from both of them. I'll get log of s square minus log of s square plus 9. So this log s I written as half log s square. I'm sure you have done it several times. So then log a minus log b will become log a by b. So it will be log s square by s square plus 9. And both limits are s and infinity. So what's the upshot of it? Laplace of 1 minus cos 3t by t turns out to be half log s square by s square plus 9 between s and infinity. Note, again, as I keep on telling, there is nothing what you have learned new here. What new thing you learned was used at this step. Laplace of somebody by t is integral of that somebody. That's all. Rest of it all is PUC integration and taking limits and how to evaluate these functions and things like that. So you must, if you are not familiar with what you have already done in class 12, these things look very scary. If you know that, then it's just hardly any effort. So how to do this? Log of s square by s square plus 9 from s to infinity. So that's what this is. Log of Laplace of 1 minus cos 3t by t is half log of s square by s square plus 9 between s and infinity. So this is nothing but I try to put s equal to infinity, but I cannot put s equal to infinity directly. So what do? I take limit of this whole expression as s tends to infinity minus s I can put directly. It's a finite number, so I'll just put it there. Now how to evaluate this? I have already shown you one similar example, not quadratic, but it was a degree 1 equation, degree 1 expression. This is also very similar to that. Basically, what do you do? Yes, how do you evaluate this limit? Yeah, many of you might have guessed it correct. You basically divide numerator and denominator by s square, so that I will get 9 by s square here and 1 here and 1 here. So when as s tends to infinity, 9 by s square tends to 0. So I get a 1 here and a 1 here, which is basically 1 by 1 is a finite number. So that's precisely what I have done also. Second expression, there is nothing much to do. Just retain it as it is. So first expression is half limit of logarithm of 1 by 1 plus 9 by s square. Basically, I divided both numerator and denominator by s square. And then let s tend to infinity. If I let s tends to infinity, this s square also goes to infinity. 9 by s square becomes 0. So 1 plus 0. 1 by 1 plus 0, which is 1. So log 1. Log 1 is correct, 0. So log 1 is 0. I get minus half of log of s square by s square plus 9. I don't like minuses. For some strange reasons, people don't like minus. It's negativity. So you take that negative thing inside. which means it is log of s square by s square plus 1 whole to the power of minus 1, which means reciprocal. Here also we don't like minus 1, so we put it the reciprocal of it. So it will be half log of s square plus 9 by s square. Don't try to simplify this, leave it as it is, because this is just a number log of something. So you can't simplify this further. So this is the answer. So I just wanted you to understand again in this solving this problem, what you learned in this semester was only this equation, this equality. Laplace of ft by t is integral of Laplace of ft from s to infinity. All your whole of your effort is, apart from remembering this formula, is how to evaluate these integrals, which you must have done in your class 12. As you can see, I am not doing very non-trivial integration here. But you have to play around with these functions, particularly log is very innocuous, and you never know when it will get complicated, when it will be simple, straightforward. So please go through this example again. These are examples which examiners like. Means I have already shown you previously e power at minus e power bt divided by t. So I thought I'll show one with trigonometry. Trigonometry also I'll show you actually some sine 5t divided by t, how to do it. But that was also straightforward because I had to integrate once and I got it immediately without log. Now I got log, so I needed to use this limit concept. So I wanted to just expound on that. I wanted to illustrate that to you, so I took this example. Okay, let's proceed. After that, what did we do? We saw periodic function. I think I spent a lot of time in periodic functions and their Laplace transform, more or less more than an hour. I think I will not tell anything further. I will not give any particular example now because we have already seen several examples. So let me just recall what does this formula say. This formula says Laplace of, if f is a periodic function with period t, you know, understand what it means. It just means f of small t plus capital T is f of t for small t for all small t. That means after every capital T, f repeats itself. Classic examples for sine and cos. We also saw some other examples, like artificial examples like some f of t is 2t up to 1 and afterwards it is 2 and then again f of t plus 2 is 2 and things like that. So they are all periodic functions. And Laplace of periodic function is given, here's the formula, 1 by 1 minus e power s capital T. Note this capital T into integral of e power minus st ft dt, integration limits from 0 to t. The most important thing to note here is, you see on the left hand side, by definition L of ft is integral of e power minus st into ft, limit varying from 0 to infinity. So left hand side is an integration with limits from 0 to infinity, infinite limits. Whereas right hand side is a finite limit. So an infinite limit you are reduced to a finite limit. So that is the power of this formula. That is possible only because it's a periodic function. So what happens at infinity to a periodic function is captured in what happens in some finite part. That is what we exploited here. So Laplace of ft of a periodic function f with period t is 1 by 1 minus e power s capital T into integral of e power minus st ft dt, integration limits from 0 to capital T. So this I will not show more examples because I think I showed you enough examples last time. Step function. This is very important, and probably even though you have an inkling of this kind of thing, this notation was new to you. This Oliver Heaviside function or step function or unit step function is called. So we define this as ht minus a is 0 if t is less than or equal to a and 1 if t is not equal to a. So remember, this is a funny way of defining the function. Normally I would say h of t. Here now I'll say h of t minus a. Many places, you know, mathematics in fact they don't use this. We use notation like h sub a of t. So that h sub a will tell me what a is. For example, h sub 2 of t is 0 till t is 2 and 1 after t is 2. But this is the standard notation for engineering. And this is also equally used. So why I am telling you this is you might get confused here. Why am I writing h of t minus a? Normally I will write if it's a function, I'll write h of t, right? Why am I writing a? That is just a notation, that's all. You could have as well written h a way of t and given the same definition, no problem. But this notation has some advantage, as we have seen in some problems before. And remember, xt minus a is to be thought of as a switch which was off till a, and at a it became on. It's not a periodic thing. At a it becomes on, and we don't know when it becomes zero. To make it zero again, I have to do something else. I'm not doing that right now. Mhm. So this step function is like a switch. Is actually a switch, and mathematical analog of a switch is basically this step function or Heaviside function. What was important about it? The most important thing was Heaviside shift theorem, which is Laplace of f of t minus a into h of t minus a is e power minus as L of ft. That is what uh, is the formula. It's a very easy formula. It's not at all difficult. If you understand what these functions are, it's very easy. Just follows them straight from the definition. But these proofs are not in your syllabus, so I won't write the proof. But you must remember this. What is it that you have to observe here? You have to find Laplace of f into h, where f and h both have same argument. That was one reason why I wrote h in such a funny way, not h sub a. Only for mathematics we would have done that. But engineering people have this notation. F of t minus a into h of t minus a. Laplace of that is Laplace of ft. If I know Laplace of ft, I know Laplace of f of t minus a into h of t minus a. All I have to do is multiply Laplace of ft by e power minus as. And if I get a, that is this a. This a, again I am emphasizing, f argument of f and argument of h both must be same. For example, if it is f of t and h of t minus a, this formula is not true. So all our efforts are towards making this argument also t minus a. We have seen several problems, at least one or two problems in this direction. So let me illustrate this once more. And also I promised that I will illustrate a problem with when function has three pieces like this. I want to find Laplace transform of this function where from 0 to 1 it is 1, 1 to 2 it is t, and greater than 2 it is t square. Maybe I have 10 minutes. I will maybe it will not take much time. I will quickly show you how this function looks. It's not very difficult, I'm sure you know it. From 0 to 1, the function value is 1, and from 1 to 2, function is t, and 2 onwards, function is t square. So let me show you the plot of this graph. The computer is slow, so it takes time to load this GeoGebra. This is a very interesting graphing calculator. You can, of course, put it on your computer or on your mobile. So what this function was, it's equal f of t is 1 between 0 and 1. So I will not spend too much time. I will quickly draw this graph. So 0 and t, 0 and between 0 and 1, including 1, excluding 0, the function is 1. So that means from here to here, including 1 and excluding 0, the function value is 1. So I will not use strictly function part now, but I will do an easier one for me, which is basically show you this, no problem. So try to see, this is what a function is from 0 to, right? And from 1 to 2, it looks like t. That means it looks like straight line from here to there. 1 to t. So 1 to 2. So 1 to 2, it's a straight line like this. Right? This is what it is. So I don't want the G to be showing this. Like that. And I don't want this. Okay. So this is how it looks between 0 and 1 and between 1 and 2. And what else? Between greater than 2, it looks like t square. The plot So greater than, it's not a straight line. So I plot it for you. Function here, t square, and start value is 2, and end value is say 21. So I have made a mistake. Um, Let me check this function once more. Oh, t between 1 and 2 it is t. So at 2 it should have been 2. 2 is 2. Yeah, correct. T square. Yeah, okay. This is correct. What I have done is correct. No problem. So let us try to. This function is correct. See, this function is 1 between 0 and 1, t between 0 and 2, 1 and 2, and t square beyond 2. So clearly this is not a continuous function because you see at t equal to 2, left hand limit is 2 and right hand limit is 4. That's correct. So no problem. This is what I have drawn is correct. So let me show it to you slightly. So this is how the function looks like. Okay, from 0 to 1 it is constant, 1 to 2 it is constantly increasing same slope, from 2 onwards it is 2 equals t square. So this is the function. So this function, of course, you don't need to plot these graphs for your examination, but it helps to know these kind of graphs. You understand what you are trying to do. So for this function, which looks like this, that means signal is constant from 0 to 1, from 1 to 2 signal is constantly increasing, from 2 onwards it is increasing but at a much higher rate. This is what this function is. I hope that is clear to you. So this function, I want to find the Laplace transform of this function. How do I do that? So I'd promised this kind of thing where function has 3 different forms in 3 different patches. So in this case, for the patch 0 to 1, function looks one way, patch 1 to 2 it looks another way, patch 2 onwards it looks yet another way. So that is why this is a different kind of function. So I want to find Laplace transform of this. So I want to find Laplace transform of this. So how do I do that? I showed you this. This I told you orally. I will just continue from there. I will not prove this kind of thing. F of t is this function f1 plus f2 minus f1. f2 is t and f1 is 1. So t minus 1. H of t minus a. A is 1. T is the first place where function is changing is 1. So t minus 1 plus f3 minus f2. That is t square minus t into h of t minus 2. 2 where I got this one. Observe this. What is this? Say for example, t is between 0 and 1. H t is between 0 and 1 means less than 1. So t xt minus 1 is 0, xt minus 2 is also 0. So both these are 0. I get 1. So t between 0 and 1, I get between 1 and 2, this is 0, this is 1. xt minus 1 is 1 because t is between 1 and 2 means it's bigger than 1. So this is 1, but it is less than 2, so this is 0. This is 1 means this product will become t minus 1. So 1 plus t minus 1, 1 will get cancelled and it will remain with t. So t when it is between 1 and 2, the value of the function is t. And if t is greater than 2, t is greater than 2 means it's definitely greater than 1 also. So xt minus 1 is 1 and xt minus 2 is also 1 because t is greater than 2. Both these are 1 means I get 1 plus t minus 1, where 1 will get cancelled, I get only t. T plus t square minus t, t will get cancelled and left with t square, that's what I get. So for this, how to find Laplace? So, okay, so you understand this function in 3 pieces, I can write it in one form. That is the advantage of Laplace Heaviside function. So now if I want to find Laplace of this, I write the expression Laplace of t, use linearity, use Laplace of 1 plus Laplace of this plus Laplace of this. Laplace of this is very easy to find. We already know Laplace of 1 is 1 by s square. Laplace of this, I'll use that formula. He said the shift formula. Laplace of f of t minus a into h of t minus a is something. I know. If I know Laplace of ft, I know. So I can find that. And this one is the problematic part. The first two expressions are easy to find. This one is not. You see, if I write ft is equal to t square minus t, ft and ht minus 2, they are different arguments. I want the same argument. So what do? I write t square minus t in terms of t minus 2. How do I do that? I have done it here. You can see, yeah, this is what we want to do. So t square minus t, I basically replace t by t minus 2 plus 2. So I'll get t minus 2 plus 2 whole square minus t minus 2 plus 2. Evaluate it in get a square, t minus 2 whole square. There's no square from here, so it is 4 2 minus t minus 2. So I get 3t minus 2, and here 4 minus 2. So I have done this thing. So t square minus t is nothing but t minus 2 whole square plus 3t minus 2 plus 2. So this is how I write my bad looking function in terms of the way I want it. So then L of ft is nothing but, this is what we saw, L of 1 plus L of t minus 1 is t minus 1 plus L of t square minus t is t minus 2. T square minus t, now I can write it like this. So if I write like that, this is Laplace of 1 is 1 by s, Laplace of t minus 1 is t minus 1 is e power minus s L t. This is the formula which I told you, e power minus a s, a is 1 here. Laplace of ft, f here is t, because this is ft minus 1 is t minus 1, so ft is t, so Laplace of t. Here I'll write this is my function now, something square plus 3 times that same something plus 2. So t something square plus 3 times that same something plus 2. So t square plus 3t plus 2. Laplace of this. This is easy to find. Yes, I don't think I should be spending time on how do I find this, because these are all directly written using linearity. I hope I have come to the end of this session. Yeah, it's 4 o'clock and then I'll stop here now. I hope I have given you a reasonable review of Laplace transforms, all kinds of various kinds of problems I have shown. Next is inverse Laplace transform. We'll do that from the next class. Thank you for your attention.